Alright, everybody. Welcome to 15.1, which is entitled Properties and Detection of Sound. We're going to be talking about sound, what it is, how fast it goes, why it goes the speed it goes, some interesting phenomenon, what makes sound loud and soft, how do we physically hear things, the scale, the decibel scale, pitch, why things sound certain sounds, and then lastly, the Doppler effect. What is it? So that's where we're going to get started. So first of all, sound. What sound is? Sound is a pressure variation transmitted through matter. A pressure variation that's transmitted through matter. It's a longitudinal wave. It's a wave that like you can see here, a tuning fork pushing and pulling on the air. Now, when a tuning fork compresses the air, that's called a compression. These dark lines that transmit to the right are called compressions. Or it can stretch out, and these are called rarefications. These are the spots in between. Now, your ear can sense both a push or a pull. Now, they have the same properties, meaning they bounce off, they transmit through. We can hear people through doors. We can hear our echoes, reflections, and transmissions. Now, I've got a link to a picture here of a bell, and it shows like a bell ringing. So here's a bell ringing, and you can see all sound, every single sound. There isn't a sound made that doesn't come from a vibration. So you see this bell vibrating, and it's physically pushing and pulling on the air molecules around it. And those pushes and pulls transmit from the bell through the air into your ear. So if there was no air between the bell and you would hear no sound. The speed of sound. The speed of sound is 343 meters per second, and it depends on a couple of things. How fast sound travels, first of all, depends on what it's going through. It travels through metal and water a lot faster than it travels through air. It depends on the temperature. The hotter it is outside, the faster it travels. Think about absolute zero. Absolute zero is where things don't move. The pressure. If you put more pressure, more molecules, it can travel faster to it. Or on the other side, if you took all the molecules out, we wouldn't be able to transmit a pressure wave. And the speed of sound we accept is 343 meters per second. Now that's at 1 atmosphere pressure, so that's at sea level and roughly 68 degrees Fahrenheit or 20 degrees Celsius. This is the speed of sound in different media. You can see in air it's typically 343. If you get colder, it goes slower. And then we've got over here water and then salt water. Salt water is more dense, and then rubber and then iron. So it can travel a lot faster through a lot of different medium. For instance, lightning followed by a thunderclap. I've got a video that I'd like you to check out now. It's entitled 100 tons of TNT, and you can physically see the difference between the speed of light and the speed of sound, and the speed of sound through air, through the speed of sound in under the ground. So I'll give you a moment to go check that out. Check out the link here. The next thing I want to talk about is loudness. Why does certain sounds sound loud? And loudness is due to the amplitude. So the bigger the push of air coming in, we perceive that as louder. Not the faster waves coming in faster. It's amplitude. Your ear can detect a pressure difference of 1/billionth of an atmosphere. So like when you go over a hill, you go flying, you go swimming, you'll feel that pressure pushing or pulling on your eardrum. And there's a huge spectrum, and it's called a logarithmic spectrum, the decibel scale. Come over here and I'll show you the decibel scale. The decibel scale, if you look on the far left, this is like 0 decibels. 20 decibels is whispering to one another. 40 decibels is study hall. 60 decibels, normal conversation. So me talking right now, that would be considered around 60 decibels. I've got a decibel scale in my classroom that I'll show you when you come in. And notice that these numbers go up by 20 every time. So 20, 40, 60, 80, 100, 120, 140. So they're going up linearly. Look over here how the actual pressure wave gets 10 times bigger. So you're not just going up by counting up 20, you're getting 10 times bigger, 10 times bigger, 10 times bigger. So look at the difference between whispering at 1 meter and study hall. That wave is physically 10 times bigger. Whispering at 1 meter to normal conversation, that's 100 times bigger. Whispering at 1 meter and busy traffic, so 10, 100, it's 1,000. The wave is physically 1,000 times bigger when you're talking about a 60 decibel increase. So you're going up 60 decibels, but it's literally 1,000. So that's what we call a logarithmic scale. Now, I've got an animation of how your ear works. In your book, there's this diagram, but hearing is a really wonderful sense. It's the only one of our senses that's what's called mechanical. It uses moving parts. So you've got this outer part of your ear here that funnels pressure waves into your tympanic membrane. Now, your tympanic membrane is this blue thing that's going in and out. Now, your tympanic membrane gets sucked out by rarefications and pushed in by compressions, and those are transmitted into the 3 smallest bones in your body. And those 3 smallest bones push and pull on a sac-filled fluid called the cochlea. Now, the cochlea is what we take advantage of when we spin around in circles and you get dizzy. Gravity pulls the fluid straight down, and that's how we can tell up from down. And we spin around and we screw that up. Also, if you get intoxicated, alcohol permeates inside of that cochlea, and that makes there's little tiny hairs in there, and that difference in density makes the hairs float or sink depending upon how much alcohol you have, and that's what gives you that dizzy feeling when people drink. It's due to that permeation of the inner ear. And then it goes into your brain. So then that cochlea sends a signal via your auditory nerve, and your hearing, you hear that as sound. Now, you've probably undoubtedly heard the thing, if a tree falls in the forest, does it make a sound? Well, it depends on what your definition of sound is. Because we call sound sound because human beings hear it. There's stuff happening all the time that we don't hear, and we don't call it sound because we don't hear it. Next, we're going to talk about pitch. Pitch, like what physical note that you're hearing, is known as pitch, and that's frequency. Like the human range of hearing goes from 20 hertz, that's like the deep rumbling bass, up to 16,000 hertz. That's that high-pitched squeal you hear when you turn on a television, like the old school TVs. Or if you've got one of those like ringtones, like the mosquito ringtones, those are up there. I'll test your hearing in class so you can kind of see. Old people, they lose their hearing above 8,000 hertz, which is why it's hard to decipher. Old people are like, huh? It's not because they can't physically hear the volume, they can't hear the pitch. And human speech encompasses a lot of high frequency tones. On the right, you'll see I've got a bunch of notes and the corresponding frequencies. There is human hearing encompasses a certain bandwidth. Like I said, it's like 20 hertz down here and 16,000 hertz up here. Now, there is stuff above what we can hear, and we call it ultrasound. There is sound above what we hear, and that's called ultrasound. And there's sound below what we can hear, and we call that infrasound. Just like you've probably heard of infrared, ultraviolet, it's the same idea. Infrared is colors that are below what we can see, and ultraviolet is colors above what we can see. So, ultrasound, infrasound. And the last thing I want to talk to you about, just introduce you to, is the Doppler effect. Now, the Doppler effect is an apparent change in the pitch when something moves towards you or away from you. And I've got some examples I'm going to put up that I want you to watch. There's two videos. There's a video of a guy on skis playing the trombone coming down the hill, and there's a video of a train whizzing by a guy playing a train horn. And those are examples of the Doppler effect. Now, the Doppler effect stems from the fact that the speed of sound is constant. Now, I've got an animation here I want to show you if it loads up. Right here. So you'll notice, I'll slow my dot down. Over here, you'll see an object that's giving off sound. And the object is standing still. Now, if I move the object, and these sound waves are traveling away from the object at 343 meters per second. Now, if I move my object, let's say at 60% the speed of sound, so like roughly like 200 meters per second, you'll notice, now I'm going to pause it, you'll notice that the waves over here are compressed, and the waves over here look like they're stretched out. So in front of this object, we hear a higher pitch. The waves are closer together, and we call that a higher frequency. On the back side, you'll notice that the waves are stretched out, and that's a lower frequency. It's this akin when you listen to little kids when they're playing with cars, they go meow. That's the Doppler effect. That meow, the high pitch, low pitch, the Doppler effect. Now, really interesting stuff happens when we start traveling at the speed of sound. So I can up my, I'm actually going a little bit faster. This is called Mach 1. Going at the speed of sound is Mach 1. And you'll notice that all the sound waves reach this. We'll talk about this a little bit, and then I'll give you another. I'll link you to this website so you can play around. What if you went as fast as you can go? We're going Mach 2 right now. What that looks like. And you'll see some interesting videos dealing with going what's called supersonic, going faster than the speed of sound. So the Doppler effect. When you move towards something, you have a higher frequency. When you move away from something, it's lower frequency. It deals with the relative motion between either the detector or the emitter. There's an equation that deals with the Doppler effect. It is right here. FD, the D stands for detector. The S stands for source. V stands for velocity and F stands for frequency. So you can calculate the frequency shift from this equation. All right, this has been 14.1. We've talked about what sound is, how the speed of sound is affected by different things, how we hear sound, what it means to be loud. Loudness is higher amplitude. It's by the decibel scale, which is logarithmic. The pitch is frequency, how frequent the waves are getting to me. And then lastly, the Doppler shift. We get an apparent shift in hearing from relative motion between the observer and the transmitter.